Welcome everyone. Today we're going to deconstruct the intelligent brain behind modern data center cooling. That's the control logic of the coolant distribution unit. We're going to break down exactly how these systems think, how they decide, and how they act to protect billions of dollars in IT hardware. So here's our game plan for this little mini course. We'll start with the fundamentals, what a CDU even is and how its control system works. Then, we're going to build on that, looking at the specific modes an operator can choose. We'll explore some really cool advanced strategies for safety and efficiency, and then we'll wrap it all up with the key takeaways.
All right, first up, what do we actually mean when we say control logic? Well, in simple terms, you can think of it as the pre-programmed rulebook that lets the cooling hardware react instantly to a changing environment. In a world of high-density computing where temperatures can spike in a matter of seconds, this isn't just some nice-to-have feature. It is the system's core survival mechanism.
As you can see right here, the CDU is basically a sophisticated thermal middleman. It sits right between those scorching hot servers and the main building's water supply. The whole job of the control logic is to manage this heat exchange with absolute precision. And, this is critical, it makes sure the specialized coolant for the servers and the building's water never actually mix. That's a huge deal for protecting all that sensitive IT gear.
So how does this control logic actually work? What's happening under the hood? Well, at its heart, every single control system, from the thermostat in your house to this advanced CDU, it all relies on one really powerful principle: the feedback loop. This is the secret sauce to how any system can self-regulate.
This sense, decide, act loop is just constantly running over and over again. So imagine your server load suddenly skyrockets. The CDU senses that the coolant temperature is rising. The controller then decides this is way above its target set point, and instantly it acts. It tells a valve to open up a little wider or a pump to spin a little faster, bringing that temperature right back in line. This simple loop is the entire foundation of its autonomous operation.
Right, so you might be wondering, what kind of algorithm is actually running inside that controller? How does it know how much to adjust a pump or a valve? If it reacts too aggressively, it could overshoot its target, cause all sorts of instability. But if it's too slow, the IT equipment could overheat. It's a real balancing act.
Well, the answer in most of these industrial systems is this brilliant algorithm called a PID controller. Think of it like driving a car. The P for proportional, that's your foot on the gas. The further you are from your target speed, the more you press down. The I for integral, that notices if you're consistently just a little bit too slow. Maybe you're going up a hill, and it adds a little more gas to compensate. And then the D for derivative, that's you looking ahead. If you see a downhill slope coming, you start easing off the gas before you even start speeding. All three of those terms working together allow for incredibly smooth, incredibly precise control.
And this is where all that theory becomes practice. On the left, you're looking at the real-time sensor inputs the controller's watching, things like humidity and temperature. On the right, those are the targets, the set points that an operator plugs in. That PID logic we just talked about, that's the engine in the middle, and it is constantly, relentlessly working to make the real-time value on the left match the target value on the right.
Okay, so with that foundation in place, now we can check out the three primary ways these pumps are actually told to behave. An operator can pick a control mode based on exactly what the IT hardware needs, and each one has a totally different objective.
This slide really shows off how flexible the system is. An operator has three main options. They can go with a simple fixed speed, which is basically like putting it on cruise control. Or they can choose fixed flow to absolutely guarantee a specific volume of coolant is moving every single minute. Or, and this is really important for big deployments, they can use differential pressure, which cleverly makes sure that even the servers at the very end of a long row get the exact same cooling pressure as the ones right next to the CDU. Pretty smart.
All right, so now let's explore the advanced strategies, the stuff that turns a simple cooling loop into a truly intelligent protective system. You can think of these as extra layers of logic that are built on top of that basic feedback loop to handle much more complex situations.
Let me tell you, condensation is the absolute enemy of electronics. So to fight this, the CDU has this incredibly important safety feature. It is constantly monitoring the room's temperature and humidity to calculate the dew point. That's the exact temperature where condensation is going to form. If the cooling target gets even a little too close to that dew point, the control logic automatically steps in and raises the coolant temperature, which prevents catastrophic moisture from ever forming inside that expensive IT gear.
Now, for these really big, large-scale deployments, you almost never have just one CDU. That's where group control comes in. It allows a whole fleet of CDUs to operate together in unison.
One unit gets assigned the role of principal, it's the leader, while all the others become agents. And this setup gives you both redundancy and perfectly synchronized performance.
So here's how that looks in the real world. The principal CDU, it acts like the conductor of an orchestra. It broadcasts its settings, the control mode, the temperature set points, and all the agent units automatically follow its lead. This makes management so much simpler, letting an operator control the cooling for an entire data hall from just a single interface.
This group setup also creates this really powerful automated failover system. So if the principal unit suddenly goes offline, another CDU can be automatically promoted to take its place. In some setups, you can even have standby units that will just activate and pick up the cooling load if any of the active units fail. For a mission-critical data center, this kind of redundancy is absolutely non-negotiable for maintaining uptime.
Okay, wow, we've covered a lot of ground, right? From the basic principles all the way up to advanced failover strategies. So let's just take a second and boil this whole mini-course down to its most important points.
So if you walk away with just these 3 points, you are going to have a really strong foundational understanding of how these complex systems operate. Number 1, at its core, it's just a sense, decide, act loop. Number 2, that loop is used to execute one of 3 main control modes. And finally, number 3, a bunch of sophisticated logic for safety and redundancy gets layered right on top.
And this leaves us with one final, forward-looking question. The logic we've been talking about is incredibly powerful, but it's mainly reactive. It responds to changes as they happen. The next frontier, which is already being explored in research labs, is AI-driven predictive cooling. Just imagine a system that uses reinforcement learning to anticipate a massive computing job, and it pre-cools the system moments before that thermal load even hits. That's the leap from just reacting to the present to intelligently preparing for the future.